Look at the physical world around you, from the gasoline in our cars to the synthetic fertilizers keeping our food supply stable. 90% of all industrial products rely on a single hidden engine, catalysts. But while these materials drive manufacturing on a massive scale, the actual chemical work happens on a stage far too small to see, down at the atomic level. For 50 years, chemists have operated under a strict rule known as surface science. It is the belief that reactions only happen on the extreme outer edge of a catalyst, leaving the massive interior dark, inert, and chemically useless. Even when researchers studied spillover, the exchange of atoms between a metal and its support, they assumed it was a surface-only phenomenon. This diagram shows atoms sliding strictly along the perimeter boundary, unable to penetrate the solid core. By accepting this boundary, engineers have spent decades obsessing over that outer 1% of the material, while leaving 99% of its potential trapped and dormant inside. Our reliance on this two-dimensional model has hit a physical wall. We can no longer make industrial processes more efficient simply by trying to maximize surface area. But what if that dark, inaccessible 99% isn't actually a dead zone? Breaking the industrial bottleneck requires looking past the surface skin and seeing directly into the solid heart of a crystal, a feat previously thought impossible. Researchers at the Dalian Institute of Chemical Physics decided to test the limits of that 50-year-old surface dogma. They focused their study on a specific catalyst, ruthenium metal supported on a crystalline lattice of rutile titanium dioxide. To see the reaction in real time, they used environmental transmission electron microscopy, a tool capable of recording chemical movements at the atomic level. Their first observation was the interface itself. The boundary where the metal meets the support acts as an atomic scale guard, functioning like a gateway that controls entry into the material. The combination of the right tool and the right model finally allowed for direct observation of what happens when that atomic gateway opens. Increasing energy, the team captured oxygen atoms as they completely bypassed the two-dimensional surface to tunnel deep into the titanium dioxide's interior. This movement is pulled by differences in chemical potential, forcing the oxygen atoms to travel 3 to 5 layers deep into the crystal lattice. This is bulk oxygen spillover, the first direct evidence that mass can actively move through the solid bulk of a catalyst. The catalyst interior acts as a highly active three-dimensional highway system, allowing the bulk material to participate in the chemical reaction. This single observation changes the concept of metal support interactions. We now know that the boundary between these materials is not just a surface-level contact point. We are transitioning from two-dimensional surface optimization to a three-dimensional synergy between the surface, the interface, and the bulk. Watch how the active area expands from a flat plane into a volumetric cube. By engineering these internal pathways, scientists can design smarter catalysts that utilize their entire mass, breaking the bottlenecks that have limited industrial chemistry for decades. If we can master the flow of mass through these deep atomic highways and unlock the dormant bulk of our materials, could this 3D architecture provide the performance leap needed for a cleaner energy future? In Part 1, we saw how atoms establish a continuous flow across the microscopic architecture of a catalyst, but those pathways assume a strict geographic limit. It raises a question about our entire map of where this chemistry happens. Are we missing the main territory? For nearly 50 years, chemical engineering has operated under a single constraint. Catalytic reactions occur only on the outer skin of a material. Because the solid center was treated as dead space, engineers faced a stark math problem. To generate more chemical power, they had to build more surface area, which meant mining and refining vast quantities of expensive, rare metals to spread them as thin as possible. That high cost limits the scale of our technology. Relying on massive amounts of rare metals makes the process of splitting water for hydrogen or scrubbing CO2 from the atmosphere too slow and expensive to deploy globally. The transition to clean energy hit a physical bottleneck. We have been trying to solve a three-dimensional global problem using two-dimensional chemistry. Researchers at the Dalian Institute of Chemical Physics began tracking the exact movement of individual oxygen atoms on a catalyst made of ruthenium and titanium dioxide. Using an environmental transmission electron microscope, they observed a completely different pathway. The atoms breach the surface, moving directly into the solid interior. Oxygen travels up to 5 atomic layers deep into the titanium dioxide. The material boundary isn't a solid wall, but a microscopic gatekeeper. It physically expands and contracts to control oxygen flowing into the bulk. This proves the interior volume of the catalyst is chemically active. The traditional model of surface-only chemistry is incomplete. Since the interior is active, engineers can stop focusing solely on coating a structure's exterior. They must now design the entire physical body of the material. The formal scientific term for this mechanism is bulk oxygen spillover. By utilizing surface-interface-bulk synergy, researchers expand the reaction space into the third dimension, multiplying total capacity. Scientists now act as molecular architects, installing internal plumbing directly through the material's solid center. Exploiting structural volume shifts chemical design out of flatland. In this new model, density, rather than surface area, dictates the ceiling of reaction speed. This dimensional shift targets the primary bottleneck of large-scale green hydrogen production. This chart compares standard two-dimensional water splitting efficiency with the new method. By utilizing the catalyst's internal bulk flow, the team observed a 10-fold spike in overall efficiency. Multiplying the reaction speed by 10 drastically reduces the required amount of rare metals. This drives production costs down far enough to put green hydrogen on a path to compete with fossil-based gasoline. The same principle applies to carbon capture. Instead of pinning CO2 molecules to an exterior layer, these materials pull the gas deep into their internal structure to be processed through their entire body. Utilizing these internal three-dimensional pathways converts slow, theoretical clean energy reactions into rapid, industrial-scale synthetic fuels. We are entering a phase where catalyst design is defined by these deep-flow pathways. This discovery addresses the material scarcity and energy costs that currently prevent us from recycling carbon and hydrogen at a planetary scale. We have identified the hidden engine inside our materials, providing the efficiency needed to power global industry without extracting new carbon. Finding undiscovered space inside matter provides the material efficiency required to stabilize the atmosphere. Breaking past the surface rewrites the physical limits of the energy transition.